Yeah, thank you, Uli, for the friendly introduction. And yes, a new level of accuracy is promised here. And give me some minutes to show you what is meant by this. At the beginning, I can state, first of all, I totally agree to our previous speaker, resolution matters. But first of all, let me explain the theory of application on how our new developed tool is working. Our well-known and established ultrasonic inline inspection electronics send out an ultrasonic impulse, shown here, and it travels through the liquid coupling medium towards the pipe wall, is reflected there, and a part of it is going into the pipe wall, also reflected there, and we can receive the signals and measure the arrival times or the time of flights. During this, we also can monitor the liquid medium properties, especially the sound velocity inside the medium, and then, knowing the speed of sound and the time of flight, we can easily calculate the distance between the sensor and the pipe wall. And therefore, we built a new sensor carrier with a lot of ultrasonic transducers on the outer surface, and so we can monitor this so-called standoff, the distance on the whole shape. This, compared to a mechanical caliper tool, is a direct measurement of the internal diameter of the pipeline. There's no calibration process needed before a run starts, and after the run, there's no post-processing needed like baseline subtraction or normalization. Since we very well know the diameter of our tool, we can calculate the total internal bore, and in addition, as mentioned before, we get the wall thickness too. So we also can calculate the outer diameter of the pipeline. The new tool is called Atlas UG, and UG is an acronym for ultrasonic geometry. On the next slide, I can show you the final design. So, as usual, we have some supporting cups for the tool and a stainless steel body. And here we embedded the ultrasonic transducers in a row of multiple rings. And we created a certain overlap between the sensors to guarantee the total circumferential coverage of the pipe wall. And therefore, we come up with the circumferential resolution down to 8 millimeters, depending on the pipeline size and the tool size. The sensors are arranged in a three-dimensional way, and therefore, we can cover the whole pipeline. Sorry, I said that before. Doing this, having a lot of sensors in the circumference next to each other and in these different lines, we get a very precise snapshot of the internal shape of the pipeline, and in the same moment, we get a very precise information on the position of our tool inside that pipeline. So taking this data into account, we can easily calculate this position and registrate orientation and tilt angle, and therefore we can compensate typical behavior of a tool, like tool tilt, decentralization, and even vibration, since the data is sampled with several hundred hertz. So we have a high temporal resolution of the tool movement during the pass through the pipeline. While being pushed through the line, we take data points every 3 millimeters or even every 1.5 millimeter. So we have a very high actual sampling here too. And this is due to the state-of-the-art acquisition system, which is already known as the EVO series from NDT. It's the same electronics that also drives our crack inspection tools and our wall thickness inspection tools. Some advantages of this technology will be shown on the next slide. The behavior shown here on the upper right is, let's say, quite typical, or at least can happen for mechanical caliper tools. And you see that, especially at high tool speeds, these arms touching the wall might not give the correct shape of the deformation. And our technology now is a non-contact measurement, so we do not suffer from such effects, and we get, hopefully, the precise shape of this deformation. Since there's no mechanical contact between our sensor system and the pipe wall, we are quite well protected from sensor damage too. The sensors are embedded in the stainless steel body. As mentioned before, we get a wall thickness sampling too using this technology. And a small example is shown here. This is a test pipeline from our facility. There are some milled external wall thickness defects, and yeah, our logo can be seen too. And this is the final result of the Atlas data set. Of course, we do not share the high resolution from UMP Plus or from MFLA Ultra, but it's just we get this wall thickness data, and it can be used to identify certain features in the pipeline during a geometry inspection, like welded sleeves, patches, or even corrosion. Before we offered the Atlas UG service to the customer, we had some in-house qualification process. We had several artificial defects, geometrical defects like dents. In this example, this is taken from a 12-inch pipeline, since the first prototype was 12-inch. And this is a typical but very good result of this test procedure. And we see that the depth sizing accuracy for the whole range is within a sub-millimeter accuracy. On the next slide, I show you some example data, which is taken from a commercial run. Unfortunately, this defect is not verified for now, so nobody digged it out. But this is a very good-looking data set. We can clearly see the deformation. Oh, sorry. In this plot, it's this line scan plot we saw before. Distance on this axis, circumferential position on this axis. Here's a C-scan presentation of the same data set. And using this high resolution and precise data, we can also generate some nice three-dimensional plots from this deformation. And going into detail, using some interpolation, of course, at this point, you can have some great visualization of your deformation feature and clearly see the shape of this deformation. Of course, there are some verified field results too. And one of this I will show you here. This is a picture of the deformation, clearly be seen here, coming from a 10-inch line, and the depth measurement from the ILI tool, Atlas UG, and the field verification, they match on a sub-millimeter accuracy. And that's a very good result, we think. The large discrepancy in length measurement might be explained by two things. It's a term of definition. What is the length of a dent? Where does it start? Where does it end? And second thing is that we have experienced that measuring the length of a dent in field is often prone to errors. Second thing, there's a small mismatch in the clock position. This is more systematically, since this reported position is the center of the feature, meaning the deepest point of the dent, and this is the starting edge of the box or of the total feature. So that's why these numbers differ. If we go into the data set, which was taken by the Atlas tool, can be shown here. And again, we see the feature in this line scan presentation and in the C-scan presentation. And if you compare to the former shown picture, you see there are some artifacts. And that's what I meant before. This tool obviously suffered from some tool movement and vibration during inspection. So this is more like a raw data set. It's not real raw data since we measure times and no depths. But it's not further processed. So this is the direct data showing the depth profile. But the result before shows the accuracy is still within sub-millimeter during vibration. And we can handle this by post-processing as might be seen here in this visualization, the vibration of the tool can be calculated out, and the artifacts are much smaller. They're not totally gone, but they are much smaller. If we take into account all field verification results we have for now, we come up with this slide. 29 digs have been done. All 29 features were within specification. Our specification is plus minus 1 millimeter, and most NDE tolerances are in the same region. And showing this in a unity plot, as it is predicted by the Parallel Operator Forum now using this new format, showing the data points and the error ellipses. All of them are touching the red line. All of them are within specification. So all this together allows us to come up with a performance specification for the new service, Atlas UG, as shown here. We have a threshold for detecting deformation features of 2 millimeters when we have a probability of detection larger than 90% and 80% certainty, and it goes up to 2.5 millimeter if we set down if we raise the certainty to 90%. The depth sizing accuracy is stated to be plus minus 1 millimeter, length and width given here 6 and 15 millimeter respectively. So we think this is a quite competitive specification for a geometry tool. The service is available since 2016, and for now we have done nearly 3,000 kilometers of inspection. And it's a small graphics on how they are distributed around the world. So there are some free spots we can fill. And for now, the first run success rate for this service is still 100%. On the next slide, I want to show you one of the key advantages of this new service, because it can be fully integrated into our existing services like corrosion inspection and crack inspection. There's a picture of a possible tool here. So you see some tool electronics, some batteries, and then coming with the geometry tool, Atlas UG, and finally, in this case, it's a wall thickness tool at the end. And there are some benefits doing this simultaneously. First thing, you have 2 inspection results in a single run, so you don't need additional runs at that position. Second thing, since the electronics saving and storing this data are identical on the same tool, you have an intrinsic data correlation. There's no mismatch in distance measurement, in orientation, so you can easily correlate features which are deformation-based or which are corrosion and crack-based. For now, we have reported more than 250 of these combined features, or they are often called interacting threads, and 17 of them already verified. One of them is shown here, hardly to see. It's a crack field with a smooth dent. And another example is on this slide. There's extended external corrosion superimposed by a dent. Dent depth, again, fits very well within specification. And as mentioned before, in the Atlas UG dataset, this blue line represents the wall thickness sampling. There, the effect of corrosion already can be seen. Of course, the sizing of the corrosion is then done by the ultrasonic metal loss tool at the end of the ILL tool. So, next slide, I come up with very, very recent results we received from a field verification campaign in the US, some laser scanned data of deformation. Not sure if it can be seen on the beamer. Here is the deformation. It's a 16-inch pipeline, and it's that recently this data set analysis is still going on, but I can show you some first results. If we take the laser scan and visualize it in the same way we can visualize our data set, we come up with these two plots. This is the laser scan data with very high resolution, even higher than this 1 or 2 millimeters mentioned before. And this is our data set with the given resolution of 3 millimeters axial and 12 millimeters circumferential. So we have, on the first view, a very good agreement, but there are no numbers here. And I will show you on the next slide what the result is. If we take the data on a line, actually through the pipeline, going through the deepest point of the DENT in the laser data set and in our data set, and keeping in mind that one data was taken from the outer side of the pipeline and the other data set from the inside of the pipeline, we come up with these plots. The red line is the laser. Then we can add a wall thickness. In this case, it was measured to 7.6 millimeters. And the blue line is the result of the inline inspection. We see a very good agreement of both data sets. Of course, both data sets here are they're centralized to the deepest point, because on the laser scan, there's no global distance of the pipeline where the defect is. But showing these two lines, a very good agreement. We can see there's a slight asymmetry in the DENT in both data sets. So we really believe that we measured the shape very, very well. That brings me to the next topic. What can we do with this data, with this high resolved and precise data? And I want to talk about DENT assessment. And in the recent past, the assessment methodologies have changed or were developed further. Formerly, just the depth was the main parameter to monitor the strengths of a feature and to decide what will be the next steps. But new methodologies use more. They use the shape of the DENT. And one example will be the fatigue life assessment from MD49 from the PRCI. And this is a small sketch. Basically, what is done here, you need the shape of the DENT in axial and circumferential direction, and you extract some certain depths and lengths and width parameters of this feature to do further calculations. Second example will be strength calculation, which is really based on the three-dimensional data set. So the example I have for you is the comparison between an identical DENT we found during a commercial inspection, and we were lucky to be in that line 2 weeks before with old-fashioned mechanical caliper tool and with our ultrasonic Atlas UG tool. The depth sizing works fine for both, and within an accuracy of plus minus 1 millimeter, they agree. Length measurement, I mentioned before, always not that easy to define the starting point. The depth resolution is different in both data sets, so it's not always clear where is the first indication of the starting point of the DENT. And the discrepancy in width can easily be explained by the lack of resolution for this data set. You can see the deformation only on 3 channels, and here it's on more than 12 channels. So if you use these 2 data sets and do the shape-based calculations following the MD49 code and plot the relative deviation between these 2 results for a certain set of parameters. I cannot show all parameters. It's a quite complex code, but for this example, it's in upstream direction, counterclockwise, and you have this set of parameters from your 3-dimensional data set. You see relative deviations between the ultrasonic results and the mechanical results, which can be as high as 80%. And that means if you rely on a poor data set, your next decision might be wrong, and the assessment of the DENT might be not that critical or more critical than expected. Second example I want to show you, strain assessment, strain calculations based on these two data sets. First of all, we show the data set itself, the depth information, and then we can calculate axial curvature and circumferential curvature. On top is always the mechanical data set, and bottom the ultrasonic data set. What can easily be seen is that the calculation benefits from the higher resolution and the higher precision, since we get less artifacts during calculation. All plots are scaled to the full range from minimum to maximum, but the maximum values, they differ a little, and there are further calculations done: membrane strain, axial bending strain, and circumferential bending strain. Again, the difference are not that much, but they are there. And if we sum up all these strain calculations, we get this so-called combined strain, internal and external. And again, this picture is better resolved, it's smoother, more reliable, and even the final numbers differ. And yeah, resolution matters. The numbers are quite small. So I show you a table of the main results. There are deviations up to 50% during calculation, but in this case, the combined internal and external strain are the most relevant parameters, and they differ 2.7% strain for the mechanical data set, 2.3 for the ultrasonic data set, and it's a deviation of 17%. So in this case, the mechanical data set overestimates the strain compared to the ultrasonic data set. Unfortunately, this is not a verified result, so we do not know the ground truth or have any laser scan data to compare to. Yeah, finally, I can give you a short summary on the ultrasonic geometry tool. We have seen it's a non-contact method. It's a robust tool since there's no mechanical moving part inside. It's immune to exaggeration of certain features which might happen at tool overspeed or at any girth weld. The final data set has a very high precision and a very high resolution, so you can apply state-of-the-art and even progressive assessment methods and will get more reliable results. And the main benefit for the operator might be you can do the geometry inspection simultaneously with corrosion inspection and crack inspection, and therefore you can easily identify interacting effects. Thank you.